Okay, so this video I want to go over some of the key parts of the spontaneity, energy, and entropy chapter 17. And so this is just a table of contents that they all have. We're not going to, well, actually we will be covering all of the parts of this chapter. Entropy and free energy are two important things, so we will be covering them. So the first thing that I want to do is just a little bit of a review from chapter 6. So in chapter 6, and if you want, you can look back at chapter 6. Chapter 6, we first mentioned energy. And we learned in chapter 6 the first law of thermodynamics, which is the law of conservation of energy. And the law of conservation of energy says that in a chemical process, or really in any process, energy is conserved. Energy is neither created nor destroyed. Another way of saying that is that the energy of the universe is constant. Now, energy can be changed. It can be changed from mechanical to heat, or it can be changed from chemical to heat, or chemical to mechanical. So there can be a lot of changes, but the total amount stays the same. Now, we said that in most chemical reactions, the biggest change in energy is usually in the form of heat. So most chemical reactions either take in energy as heat or they give off energy as heat. And we defined a term called entropy, or I mean not entropy, enthalpy, which is at constant pressure equal to the amount of heat taken in or given off. So we know that when delta H is negative, it's an exothermic reaction, meaning the reaction gives off energy or produces energy as heat. And when delta H is positive, it's an endothermic reaction, meaning that the reaction takes in energy as heat. So in this chapter, we are going to learn how to answer the question, is a reaction spontaneous? And by spontaneous, we mean, does it occur without outside help? So when you combine two things, will the reaction take place, or will the reaction not take place? Will it take place, or will you have to do something to it? Maybe heat it or cool it to make it take place. All right, and a spontaneous process, spontaneity and speed are not really related. Spontaneous processes can be fast or slow. So if we look at thermodynamics, which is the study of energy, versus kinetics, which we studied, I believe, in chapter 12, kinetics looks at reaction mechanisms and how a reaction takes place, and is used again to find the reaction pathway. Kinetics answers the question, how fast is a reaction? Thermodynamics only looks at the initial state and the final state, and it doesn't look at how the reaction went from point A to point B. So thermodynamics is going to provide us information that's going to tell us, is a reaction spontaneous or not? So we're going to learn about a new term called entropy. And entropy is abbreviated with a capital S. The main thing you need to know about entropy is that it is a measure of disorder. So the more random a system is, the more disorder it has, the more entropy it has. And it's linked to probability, because the more likely a process is to occur, then the more likely it will be that that process occurs, or the higher the probability that it will actually occur. All right, so entropy is S. And remember, when entropy increases, it means a substance or a system is becoming more disordered. When entropy decreases, it means a substance is becoming more orderly. And again, it has to do with probability. So let's look at a gas being in a bulb. Oops, sorry. So the gas is in the bulb. And right now in the top diagram, the stopcock is closed. If you open the stopcock, the gas will move from the left side of the bulb to the right side of the bulb. And it'll continue to move back and forth until you have about the same number of particles in each side of the bulb, or in each bulb, and on each side of the apparatus. Now, the reason that it does that has to do with probability. So, if you look at the microstates, microstate is just a possible configuration. So, if you look at arrangement 1, you have 4 gas particles on one side and none on the other. Arrangement 2 is 3 on one side, 1 on the other. Arrangement 3 is they're evenly arranged. Arrangement 4 is 1 on the left, 3 on the right, and arrangement 5 is none on the left and 4 on the right. So those are the possible arrangements of particles. And to make it simpler, we're only looking at arrangements of 4 particles. Now, let's say that you separated each of those particles and labeled them A, B, C, and D. So, how many microstates would there be that gives us arrangement 2, which again is 3 particles on the left-hand side and 1 on the right? So if you look at the number of microstates, so particle A could go to the right, B, C, and D would be left. Particle B could go to the right, A, C, and D would be left. Particle C could go to the right, A, B, and D would be left. Particle D could go to the right, A, B, and C would be left. So there's 4 ways to achieve that arrangement 2, where there's 3 particles on the left and 1 on the right. So arrangement 3, I'm not going to go through each one individually, but you can see there are 6 ways to achieve arrangement 3. There are 4 ways to achieve arrangement 4, and there's only 1 way to achieve arrangement 5. So which arrangement has the highest probability of occurring? It's the one that has the most microstates. So that would be arrangement 3, which is equal numbers of particles on both sides. So I'm going to go back. So that's why the gas will expand until you get equal numbers on both sides, because that arrangement gives you the highest probability, or there's the highest probability of that arrangement occurring, as you saw from this example. Now, we're going to skip in-class exercise number 1. It's a probability exercise, and really we don't need to do it to understand the rest of the chapter. So I'm not going to do in-class exercise number 1. Now, some of these exercises we'll go over right in the PowerPoint, and then the ones that I don't go over, which will be toward the later part of the chapter, those I will do a show me and send that to you. Okay, so let's talk about positional probability. That's really the example that I just gave, kind of went over positional probability. That depends on the number of configurations that yield a particular state. So we said that state 3 had the highest positional probability in the previous example. So again, that expanded state had the highest positional probability. Now, this is important to note when we're looking at changes of state. and we're looking at entropy. Remember, entropy is disorder. So it would make sense that the more orderly something is, the lower its entropy, because the lower the number of positions or that substance can have. So if you look at the solids are very orderly. These particles do not move. So there's really only one way that they're going to be organized. In a liquid, there's more disorder. Particles are moving around more. There are more states that it can have, or more positional probability. In a gas, they're moving around the most, and so there are the most number of states that it could have, or the most number of the most number of probabilities that could exist. So the entropy of a solid is the lowest, the entropy of a liquid is next, and then the entropy of a gas is the highest. All right, so as a substance goes from solid to liquid to gas, its entropy or its disorder changes. Now, when you mix or dissolve something in water to make a solution, generally, because you have greater volume to the solid, you have more entropy. Now, this is not always the case, and we'll go through some more examples of this later. But generally, when you go from a solid being dissolved in water to make a solution, entropy is going to increase, because again, entropy is disorder. So in class exercise number 2, for each of the following pairs, choose the substance with the higher positional entropy. Okay, so positional entropy, again, is the most disorder. So we said that the entropy of a gas is higher than the entropy of a solid. It goes from solid to liquid to gas. So that one would have the highest entropy, or the most disorder. Now for number 2, we have 2 gases. But notice that the pressure of at 1 atmosphere is greater than the pressure of 1 times 10 to the negative 2 is 0.01 atmospheres. So remember, pressure and volume are inversely proportional to one another. That's what Boyle's law is. So as the pressure of a gas goes down, the volume of that gas is going to go up. So what that means is that those gas particles have more room to move around. And so they're more disordered. There's more probable states. So the gas at the lower pressure, oops, and I'm not underlining this very well, but the gas at the lower pressure is going to have the higher entropy because it has the most disorder. Okay, so let's look at in class exercise number 3, which says predict the sign of the entropy change for each of the following processes. Solid sugar is added to water to form a solution. So we said when a solution forms, disorder increases, so entropy increases. Iodine vapor condenses on a cold surface to form crystals. When something is condensing, we're going from a solid, or iodine vapor. We're going from a gas, the vapor is a gas, to we're going from a gas to a solid, and so the entropy will decrease. All right, so join in number 1. Let's look at these. It says, which of the following substances has the higher positional probability, meaning the more arrangements, the most entropy. So we said that liquid water has less entropy than gaseous water. So the answer is B. Gaseous water has the most entropy. I want to just draw your attention to these join-in problems, because what I'm showing you right now is what the PowerPoint looks like. And when you're doing the join-in problems, if you want to check your answers, in the notes of the join-in problems, there are the correct answers are listed. So that's a way to check your answers. And it also explains why that's the right answer. So when you're going back through and looking at these, if you go along, watch the PowerPoint, just switch over to the notes, which are right underneath it. And it's not in the slideshow view, but if you have it in just a regular view, you can get what the correct answers should be. Okay, so we know again that a gas has more entropy, more positional probability than a liquid. Okay, predict the sign of the change in positional probability for the process of dry ice subliming to form gaseous CO2. So we're going from a solid to a gas. The amount of disorder should increase. So the answer would be A. Positional probability increases. All right, so you should have a pretty good understanding now of what entropy is. Again, it's the amount of disorder. All right, so now we're going to apply this to whether or not a process occurs spontaneously. And that's the second law of thermodynamics. So just to review, the first law of thermodynamics says that the energy of the universe is constant. The second law of thermodynamics says that if a process is spontaneous, it results in an increase in the entropy of the universe. All right? So it means for a process to be spontaneous, the disorder of the universe increases. So our universe is naturally going from order to more disorder in processes that are spontaneous. And a way of thinking of that, a common way, is if you throw up some cards, 52 card pickup, they land all over. It's spontaneous that they land all over. They become more disordered. It's not spontaneous that they're going to jump back into your hand and reform the deck of cards. Just think of your everyday life, your house. You might clean it once a week or however often, and through the week the house becomes less and less orderly. To make it more orderly, you have to pick things up. So spontaneous processes go toward an increase in the entropy or disorder of the universe. So the entropy of the universe is equal to the entropy of the system plus the surroundings. So either the system is going to become more ordered or less ordered, or the surroundings are going to become more or less ordered. And what we want is a positive change in entropy of the universe. So we're going to look at this in a little bit more detail. Okay, so if the entropy of the universe is positive, all right, so that's this first case. That means that the entropy of the universe increases and that the process is spontaneous in the direction that it's written. If the entropy of the universe is negative, that means the process is spontaneous in the opposite direction. And if the entropy of the universe is 0, that means that the system's at equilibrium. The process does not have a tendency to occur. Right? So the forward and the opposite directions are equal. That's what equilibrium means. All right. So we've always looked at things from the point of view of the system, but now we also need to include the surroundings. So that's a little bit different. So for any spontaneous process, again, the definition of a spontaneous process is that the change in entropy of the universe is positive. So the answer is D. Only the change in entropy of the universe must be positive. It doesn't matter if the change in entropy of the system is positive, and it doesn't matter if the change in entropy of the surroundings are positive. Just means that the total change in entropy of the universe is positive. Okay, so in class exercise number 4, it says, in a living cell, large molecules are assembled from simpler ones. Is this process consistent with the second law of thermodynamics? Well, it happens spontaneously. So that means that the entropy of the universe must increase. Now the system, if you look at the cell being the system, that becomes more ordered. So that entropy decreases. But the entropy of the surroundings then must increase enough to overcome the decrease in entropy of the system so that the entropy of the universe is positive. All right, so now we've never really dealt with the surroundings before. So we're going to learn a way that we can deal with the surroundings by only looking at the system, because we know that observing a system is pretty easy. So the sign of the change in entropy of the surroundings depends on the direction of heat flow. So we're going to look at whether or not a process is exothermic, meaning heat leaves the system, or whether a process is endothermic, meaning heat goes into the system. So when a process is exothermic, we know that delta H is negative. But delta S surroundings is positive. Now think about that. Temperature is related to kinetic energy. The more kinetic energy something has, the faster it's moving. Okay, the higher its temperature. So if the system is giving energy to the surroundings, then the surroundings are getting that energy. They're going to become more disordered because they're going to move around more quickly. Now, if delta H is positive, that means that the system is taking in energy as heat. Where does it take it in from? The surroundings. So then the surroundings will become more ordered. So remember, delta H has to do with heat. Delta S has to do with order or disorder. So when delta S is positive, that means more disorder. When delta S is negative, that means more order. Okay, so let's look at liquid water becoming a gas. All right, so we know that the change in entropy of this system is positive. Okay, and how do we know that it's positive? Because we said that when a system goes from a liquid to a gas, it gets more disorder. So more disorder, delta S is positive. Now, we also know that it takes energy to make that happen. In order to boil water, to make it go from a liquid to a gas, you have to add energy to it. Okay, so we know delta H is positive, so that means that the delta S surroundings must be negative. So we know that the delta S is positive for the system, delta S surroundings is negative. So what makes this process spontaneous? Well, it's controlled by the temperature. When it takes place at a temperature that's above the boiling point, or in the temperatures above the boiling point, it's going to be spontaneous. When it's below the boiling point, it's not going to be spontaneous. So water at room temperature is not going to boil because it's just not a favorable process. It's not a spontaneous process. All right, so now we're going to actually put some numbers on delta S surroundings so that it gives us a way to kind of calculate it and to relate it to heat. So the magnitude of the change in entropy of the surroundings depends on temperature. So it says here that the change in randomness produced by heat being added to the surroundings is greater at low temperatures. So let's think of a way, let's think of this in a practical way. All right, so let's compare me and you to Bill Gates. And you know who Bill Gates is, the Microsoft guy, one of the richest people in the world. Okay. Now, if somebody said, I'm going to give you or I $1,000, that would be a lot of money to us because, you know, $1,000 is still considered a lot of money. But if somebody told Bill Gates they were going to give him $1,000, to him, that's just a small fraction of his net wealth. And so to him, gaining $1,000 is not going to increase his wealth very much. So when the surroundings are cold and you add heat to them, the change is going to be bigger than if the surroundings are, the change in entropy is going to be bigger than if the surroundings are already warm and you add heat to it. Okay? Because remember, the change delta S is the change in randomness. So, if the surroundings are already warm, they already have a lot of randomness. And so adding heat is going to increase it, but not by a lot. Not by as much as if they were cold and you added heat. Okay, so like I said, giving us $1,000 is going to increase our wealth more than giving Bill Gates $1,000. Okay, so a way of determining, I mean, we can easily tell whether delta S is positive or negative. All we have to do is look at does the system, let me back up. It's easy to tell whether delta S system is positive or negative because you just look at does the system become more or less ordered. Now we're going to look at a way of telling whether delta S surroundings it becomes higher or lower. So we're going to learn that we can express delta S surroundings in terms of heat flow. Now heat flow means change in enthalpy. And again, change in enthalpy, delta H has a sign and a number. The sign tells us whether heat is being given in or taken off, given off or taken in by the system, and the number indicates the amount of heat taken in or given off. So this is the relationship between delta S surroundings and heat flow. So the change in entropy of the surroundings is equal to the negative delta H over T. So negative change in enthalpy over T. So that means if it's an exothermic reaction, then it's going to be a negative times a negative or a positive, and the entropy of the surroundings is going to increase. If it's an endothermic reaction, delta H is positive. So it's going to be a negative times a positive or a negative, and the change in entropy of the surroundings will decrease. The amount of that change depends on the temperature because it's the change in enthalpy divided by the temperature. Okay, so now let's kind of summarize some things. So if the change in entropy of the system is positive, meaning it becomes more disordered, and the change in entropy of the surroundings is positive, the process is always spontaneous because the change in entropy of the universe is negative or is positive. If both of these are negative, then the change in entropy of the universe is always negative, because remember, delta S universe, and it's kind of hard for me, delta S U for universe is equal to delta S system plus delta S surroundings. And I'm only going to write delta S surroundings. Hold on just a second. Okay, sorry for the interruption. I got a phone call that I had to answer, but the equation that we're looking at is the change in, or the delta S of the universe is equal to delta S systems plus surroundings. So we already, and I just wanted to remind you of that. So I already looked at these first two cases, I think. So now we're going to look at cases where one or the other might be positive or negative. So if delta S, So if delta S system is positive and delta S surroundings is negative, then how do we know whether the process is spontaneous? Well, if the value of delta S surroundings is going to be less than delta S system, then it's going to be spontaneous. Because again, when you add these two, you have to get a positive number. All right, and then the opposite case would be true if delta S surroundings is positive, meaning but delta S system is negative, then the sign of delta S universe depends on which one is bigger. Okay, so, oops. In the next slide, we want to look at in-class exercise number 5. And this is an in-class exercise where you're finding the change in entropy of the surroundings. Oops. So remember the change in entropy of the surroundings. So delta S surroundings. And it's not easy to write with this because I have to write with my cursor, or with my mouse, which is actually a trackpad. Delta S surroundings, remember, is equal to negative delta H over T. So that's the equation that you're going to use to solve each of these. And so it's a really straightforward calculation. So they want us to calculate delta S surroundings for each of these. So for the first one, delta H is negative 125, and we're at 25 degrees Celsius, which again, you need to convert to Kelvin. So that's 298 Kelvin. So the answer that you get for the first one should be 0.0419. 0.0419, and then for the second one you should get negative 2.61. So what I'm going to do is I'll write those in the notes for you, so that the first process is 0.419 kilojoules per mole, or kilojoules per Kelvin. And then the second one is negative 2.61 kilojoules per Kelvin. And so again, you're using that formula, negative delta H over T. And that way, I will do some of the problems out, but this is such a straightforward problem, I don't really feel like I need to you know, write out the whole thing. All right, so let's go back to the slideshow. Okay, so now we are going to look at a way to measure the whether or not a system is spontaneous just by looking at the system, so that we don't have to worry about the surroundings anymore, because that just gets tedious looking at the surroundings. So we're going to define a new term called G. And G stands for Gibbs free energy, or it's more commonly just known as free energy. And it's used to determine if a reaction is spontaneous. And it looks at only the system, not the surroundings. So this is the formula that we're going to use. So this is the formula that you want to write down, because this is the one that you're going to be using a lot. So delta G is equal to delta H minus T delta S. So delta G is Gibbs free energy, delta H is change in enthalpy, and T delta S is the change in entropy. And all of these things refer to the system. So we're looking at the change in enthalpy of the system and the change in entropy of the system. Okay, so they all refer to the system. And in this next slide, all that they do is look at how this relates to delta S universe. And we're not really going to focus too much on this. But here is the bottom line that you need to know. And again, if you want to go through the derivation, you can, but this is what you really need to know. When delta G is negative, the change in entropy of the universe is positive. So what does that mean? It means that this process is spontaneous, because a spontaneous process increases the change in entropy of the universe. So when delta G is negative, it means spontaneous. Okay, so that's, oh, and I didn't mean to cross it out. That's the important part. When delta G is negative, it's a spontaneous process. All right, so let's look at these various combinations. And again, I think I'm going to just do this in the note section because it's easier for me to type. So I'm going to pause while I do some writing in the notes section. In the notes section, I've written the formula, except I forgot temperature. So it wouldn't let me edit it to symbols, but this should be delta G is equal to delta H minus T delta S. So we want to look at what the sign of delta G is going to be to determine whether or not the process is spontaneous at all temperatures or only at certain temperatures. So remember, when delta G is negative, it's spontaneous. So in this first case, we have delta S is positive and delta H is negative. So we have, let me go back here. All right, there we go. All right, so we've got delta H is negative and delta S is positive. Okay, so we're going to have a negative minus a positive, which is always going to be negative. So delta G will always be negative at that case. So it will always be spontaneous at any temperature, because when you have a negative minus a positive, the result is always a negative. So now in the next case, it says delta S is positive and delta H is positive. So we've got delta H positive and delta S positive. So when is this one going to be spontaneous? Well, we've got a positive minus a positive. So in order to be spontaneous, this number has to be bigger. And so what's going to make that number bigger? The temperature. So at high temperatures, this number is going to be more likely to be bigger, and you'll have a positive minus an even bigger positive, which will be a negative. And so that will make it spontaneous. Now, in the other case, in the next case, we have delta S negative and delta H is negative. So we have a negative minus a negative. Again, minus a negative is like plus a positive. So now when this value is smaller than this one, delta G will be negative. So at low temperatures, in that case, delta G will be negative. And then in the last case, we have delta S is negative and delta H is positive. So you have a positive minus a negative, which is like plus a positive. Delta G then will always be positive. So in that case, the process is never spontaneous. All right, so I'm going to go back to the slideshow. And those, oh shoot, sorry. I did not mean to play it from the start. So let's go back to where we were. I apologize for that. We had gone to here. This is where we were. So we'll play from the current slide. There we go. Okay. So this is in-class exercise number 6. And what I'm going to do is I will do this I'm going to skip some of these in-class exercises. It's really hard for me to type them out, and I will do them when I do the show me. So I'll include exercises 6 and 7 in a separate video. All right, so we'll do exercises 6 and 7 at a later time in the next video. So join in 4 for the vaporization of a liquid at a given temperature. Okay, so we're vaporizing a liquid, meaning we're turning it from a liquid to a gas. So we know in that case that delta S is negative. We also know that it takes in heat, so delta G is also negative. I mean, not delta G. We also know that delta H is, let me back up. All right, so the formula is delta H. No, it's not. Let me back up again. The formula is delta G is equal to delta H minus T delta S. So we've got a vaporization of a liquid. So that means that takes energy. Okay, it takes energy to make a liquid go to a vapor. So delta H is positive. Delta S is also positive because we're going from a liquid to a gas, which increases the entropy. So we're going to have a positive minus a positive. So we need to make the second positive bigger, meaning it's delta H minus T delta S. So T delta S needs to be bigger. So this is going to be spontaneous at high temperatures. So delta G is going to be positive at low temperatures, negative at high temperatures. Okay, in which case must a reaction be spontaneous at all temperatures? Again, delta G is equal to delta H minus T delta S. So when you have a negative minus a positive, it's spontaneous at all temperatures. So delta H is negative, delta S is positive. That's letter D, is spontaneous at all temperatures. All right, so at constant pressure, the reaction is exothermic. So we are going from 2 molecules to 1. So we're reducing the number of molecules, meaning we're making it more ordered. So this is more ordered than this. So if we have delta G is equal to delta H minus T delta S, and we know that it's going to a more orderly substance, then delta S is going to be negative. I forgot to write the delta H, but you know what I mean. This is exothermic, so delta H is also negative. So we have negative minus a negative. So that means that we want this number to be smaller than this number. And so in order for that to happen, temperature needs to be low. So it's going to be spontaneous at low temperatures, but not at high temperatures. All right. So it says when a stable diatomic molecule forms from atoms at constant pressure, spontaneously, so we know delta G is negative, and the reaction is always exothermic, so that delta H is also negative. Oh, it says the reaction is exothermic, so that meant delta H is negative. That was a pretty easy. Didn't even need to know about delta G. Okay, join in number 8. It says when a stable diatomic molecule spontaneously forms from its atoms at constant pressure, what is true about delta S? Well, it's becoming more orderly, so delta S must be negative because there is less disorder, more order. So the answer would be A. Join in number 9. If it's spontaneous, delta G must be negative. So that is also A. Now, in order for a liquid to be vaporized at its boiling point, you still need to add energy as heat. So delta H is positive because you're adding energy as heat. What's true about delta S when you're vaporizing it at the boiling point? It's going from a liquid to a vapor, so it's becoming more disordered. Delta S would be positive. Okay, because again, delta S is the change in disorder. And then for delta G, during a phase change, delta G is equal to 0. So delta G is 0 at a phase change. And again, when you go back and you watch the show me with the problems, I'll explain a little bit more about why delta G is 0 during the phase change then. All right, so the next slide goes through some similarity or some anomalies when you're forming a solution. So sometimes it's possible for the entropy to go down when you're forming a solution. Now, we would think of it the opposite because normally you're dissolving, you're pulling ions out of a crystal, and so you would think that they're going to become more disordered. But what can happen is that they can become surrounded by water molecules, especially salts that are not very soluble. And so we have to look at then both enthalpy and entropy of solution formation to see whether it happens or not. In general, if a substance is soluble, the entropy of the solution is greater than the entropy of like the two separate things. But that again, it just depends. All right, so it says for the dissociation reaction of the acid HF, delta S is negative, meaning when HF dissolves in water, it actually becomes more ordered than it is in the crystal. And it says, why is that? And the reason would be that the ions are hydrated. They're surrounded by water molecules, and so they have a very orderly arrangement. Okay, so we already kind of have looked at entropy changes in chemical reactions. Again, the more possible configurations that it has, the higher the entropy. So in this case, when you synthesize ammonia, you're going from 4 molecules on this side to only 2. So you're going from less order to more order, so the entropy would decrease. All right, so when you have a, a reaction where everything is a gas, then the side with the greater number of gas particles has a higher entropy. And again, if you look at this diagram, that explains it. You can see there's more disorder, more possible arrangements on this side than there are on this side. So it says predict the sign of delta S for each of the following reactions. So in this case, we're going from a solid to a solid and a gas. A gas has more disorder, so we would expect delta S to be positive. The oxidation of SO2 in air, again, you've got 2 plus 1 is 3 gas particles going to 2 gas particles, so delta S would be negative. So in this one, you're going from 0 to 1. Delta S is positive because and in this one you're going from 3 to 2, so delta S is negative. Okay, so now we're going to look at some ways you can actually calculate the entropy, and because again, we want delta G to be negative, so in order to calculate delta G, we need values for delta H and we need values for delta S. So it says the third law of thermodynamics says that the entropy of a perfect crystal at 0 Kelvin is 0. So entropy increases with temperature. There can be 3 types of motion: vibrational motion, which would be just the atoms vibrating; rotation, where they rotate; and translation, which would be from point A to point B. So you see HCl at 0 Kelvin, everything is orderly, and as it rises above 0 Kelvin, the molecules start moving, and so there is less order. Okay, and then it says H2O can vibrate and rotate in several ways. So this would be vibrational. Visualize the bonds as springs. They vibrate. And then rotational, meaning the water molecule can turn. And then translational just means it could go from point A to point B. So the water molecule could move from here to here. Okay, so just like back in chapter 6, we looked at standard enthalpy values. There are standard entropy values. And you want to look at, I've posted a chart on Canvas, which I took from OWL, and you may have a copy of it from chapter 6. I'm not positive if I gave it out then or not, but it's a table of thermodynamic data. It's pretty long. It's like 11 pages, but it's on Canvas, and it says table of thermodynamic data. So it goes through and it gives you delta S values. I'll see if I can bring up what it should look like. So I've brought it up on my desktop. but this is what's posted on on Canvas. It's a table of thermodynamic data. You notice here's the standard delta H of formation. These are the standard delta S's. So remember, we said that the formation of a pure crystal at 0 Kelvin is 0. And then we're also going to use standard delta G values. So this chart is about 11 pages long, but it gives you the delta H, delta G, and S for really any substance that you would need. And it's in alphabetical order. Okay, so I'm going to go back. Right, so again, we said those standard entropy values represent how much the entropy increases. Again, when you're going from 0 to a temperature above 0. And the temperature that we look at is 23 degrees Celsius, which is 298 Kelvin. So those standard entropy values are the amount of entropy that a substance has at 23 degrees Celsius. Then what you can do is use this equation, which we first learned a variation of this equation back in chapter 6, except we used it for delta H. So the change in entropy of a reaction is equal to the entropy of the products minus the entropy of the reactants. Okay, so this is the summation sign. This is the number of moles. So it's moles of products times their entropy plus minus moles of reactants times their entropy values. And in class exercises number 9 and 10 are going to do that. So what I'm going to do is stop the PowerPoint here because I want you to go through and watch the Show Me, which will show you, we'll go through some of the in-class exercises. And then I'll either explain the rest of the PowerPoint then, or I will do another PowerPoint presentation, or I do another PowerPoint presentation like this one. All right, so you want to go through and look at the video then that explains the in-class exercises, at least through exercise 10.